Welcome student, PCH 280151 Unit 4 Marcus Huss Theory. I am Dr. Devangar Pandya from Department of Chemistry, St. Xavier's College, Autonomous, Ahmedabad. Point to discuss in today's lecture about Marcus Huss Theory. We are going to discuss the point what is Marcus Huss Theory about. Then type of barriers that require energy in outer sphere and inner sphere electron transfer. Then we are going to discuss application of Marcus theory to electron transfer reaction in donor and acceptor system. And then application of Marcus theory to bioinorganic chemistry where electron transfer take place. Let's begin with Marcus theory. Marcus Huss, that is also known as MH theory, was developed in 1956 by Rudolf A. Marcus, which explained the fundamentals of the redox or electron transfer reaction in terms of the rate of jumping or moving an electron from oxidant species electron donor to the reductant, that is electron acceptor. MH theory works as alternative Eyring's transition state theory for electron transfer reactions where bond making or bond breaking does not occur. Vibrational barrier. According to MH theory, vibration barrier exists that hampers the redox or we can say electron transfer reaction. The equilibrium structures for both the redox partners are dissimilar and the oxidation state to be changed during the course of reaction. For an electron transfer to take place, the electronic movement must be faster relative to that of nuclear movement. The vertical process features suggest that nuclear location do not change at the time of reaction. According to the energy conservation law, the transfer of electron can merely occur on the cut surface of two potential curves, whose energy is equal to that of thermal activation energy. The structure reorganization of each complex takes place by bringing the distant ligand closer and closer to distant by adjusting all the ml bond lengths to be equal to lambda I, that is inner recognition energy. This recognition is associated to facilitate the electron transfer that requires both redox centers must have a like structure during the course of electron transfer. As the vibrational barrier is proportional to the distance between redox center, the closer attachment of both the redox partners is desired to make the redox barrier low and thus electron transfer to be faster. Here you can see the barrier E act energy delta G would be there, oxidation, reduction and the electron transfer taken place in the barrier, and the energy differences is shown in this diagram. Solvation barrier. Another factor that influences redox process is solvation barrier, which is related to the organization of solvent molecules. Here you can see the molecules, cations and the double positive charge and the electron transfer determine the solvation organization, and therefore the recognition energy is going to be obtained as lambda is equal to lambda in plus observation, lambda observation. Recognition energy for inner sphere recognition energy, breathing of illustrated by this harmonic estimation, where lambda in is equal to 1/2 m omega square qr minus qi whole square. The recognition energy for outer sphere recognition energy, various polarization separations. First point in it, the first polarization, electronic polarizability with a rate of 10⁻⁻15 to 10⁻16 seconds. Slow polarization, the atomic actions such as distortion and orientation. Total polarization, fast polarization plus slow polarization, and its value would be P vector is equal to PS vector plus PF vector. The energy is required to change the solvation cell about the complexes at the time of absolute electron transfer reaction, and this energy is associated with the outer recognition energy, that is lambda O. The Marcus scale is principally based on the free energy, that is delta G, of the reactants and the products, which are roughly square functions of the reaction coordinate. Here you can see delta G star is equal to 1 by 4, 1 plus delta Z0 upon lambda is equal to lambda plus delta Z0 whole square by 4 lambda, where delta Z0 is the free enthalpy having negative value, and delta G star is the activation energy. Lambda is equal to lambda I plus lambda O. Recognition energy, the reaction profiles can be discriminated by following three ways. First one is lambda plus delta Z0 is greater than 0, that is Marcus normal region. Our rate of reaction enhances with increase in delta G0. Then B point, that is lambda plus delta Z0 is equal to 0, that the reaction rate reaches to the maximum since there is no activation barrier for electron transfer to occur and diffusion controlled reaction. And the third point, that is the lambda plus delta Z0 is lower than that of 0 Marcus inverted cases, and rate reaction diminishes since activation barrier increases. Here are the examples: self exchange reaction, that is both the way K11, the second reaction, that is a self exchange reaction 2, and the third one is the cross reaction, where the star indicates the isotope labeling. Marcus's theory for the electron transfer, a donor acceptor interpretation. Marcus' theory from a molecular viewpoint is characteristically applicable to the outer sphere ET electron transfer between an electron donor, that is D reductant, and an electron acceptor, that is A oxidant. Let us assume the donor D and acceptor A as neutral molecules to facilitate the discussion so that the electrostatic interactions or forces may be avoided. It is worth speculating and mentioning that either of the donor or acceptor may lie in a photo-excited state. Thus, there is a possibility of photo-induced electron transfer, that is PET process, to occur. In principle, the concept of Marcus model applies equally well for the electron transfer both in the ground state and excited state, except a change in energy of starting state. A reaction involving homogeneous mixture of donor D and acceptor A exhibits second order kinetics and can be divided into three steps. Step 1 is a precursors complex formation, in which the diffusion D and acceptance A having a rate constant Ka resulting in the formation of precursor complex D by A via an outer sphere mechanism. The precursor complex cleavage without electron transfer ET is illustrated by dissociation rate constant, that is Kd. So D plus A is a forward and backward reaction, Ka is for forward and K dot A is for backward, D by A. Successor complex formation, the reconstructing of the precursor complex D by A endures to form a transition state which serves as a platform for feasible electron transfer to afford a successor complex, that is D plus by A plus. The Frank-Gordon principle is obeyed right from the formation of precursor to successor complexes. Even the transition state must also be the same to form the successor complex. The third point, that is a successor complex dissociation. Eventually the successor complex dissociation take place to separate cation D plus and anion A minus. Here is the reaction for that. Overall, this reaction can be illustrated. Now in bioinorganic chemistry, application of Marcus-Huss theory, oxygen transfer during the respiration, hemoglobin act as electron carrier protein by carrying oxygen from lungs to the cell in vertebrates. Here is the oxygen carrier as Fe. It is evident from the above figure that the oxidation state of Fe plus 2 changes to Fe3 and vice versa. Likewise, O2 is reduced to O2 minus in forward step, and in backward step O2 minus is reduced to O2. If we sum up this, the fundamental of Marcus-Huss theory is given in the very first part, and the vibration barrier and solvation barriers, which needs surplus energy to facilitate the electron transfer process. Recognition of redox couples before electron transfer occurs in described and presented in the form of equations. Self-exchange reaction and cross reactions are given as example to understand the importance of Marcus-Huss theory, and the Marcus-Huss theory applied to the electron transfer process in donor-acceptor behavior has also been explained. And eventually the application of Marcus-Huss theory to the bioinorganic chemistry like electron transfer in hemoglobin has been illustrated. Well, this is enough from my end. Thank you for paying attention to this video lecture. Keep asking questions. As you know, asking question is a beautiful way to gain knowledge. Thank you.